We are live, huh? Mm, I didn't have to say it.
So I think we can start. Good evening. The last time, I think we were able to put a small bootloader. So let me just go to that folder. So we had this start.asm. And then we did we said the purpose of the bootloader is to collect system information. We haven't done that yet, but we tried to put the system in expected state. Then today we call into everything in sync. So we first disabled interrupts. I think this is common in almost all processors. You first need to disable interrupts. Then what did you do? We enabled protected mode, which is 32-bit mode. So this was, where is it here? Nope. This was enabling the protection bit. I think the last session we saw that Intel has a certain flag or leverage flag in this system register called CR0, where if that flag is set, it means the processor operates in 32-bit mode. Else, the processor operates in 16-bit mode. I don't understand the question. Could you please rephrase it?
So, kidogo tu huku jamaa hajaniita.
Smart Edge, I think you've asked a question that I don't understand. Okay, as we wait, let me just continue. Then we created these wrapper functions to read from devices. And then one of the things we did last time was to print to screen, and then we booted. So today, the last step that we need to do is to create TDT, which I didn't explain, and then we need to load the next. We need to read the next bytes of our kernel from disk into memory. Remember, said that the firmware, in this case it's BIOS, will only load 512 bytes of our operating system, but 512 bytes is not enough to write even the basic operating system. So we need to load the remaining bytes into memory to do those things. So let me just write them down. Today what we'll do is load GDT, load understand GDT. Let me begin understand. Load GDT. Then then what will we do? We can read the disk. Then jump to protected mode. We can first jump to protected mode, then read the disk, or we can read the disk, then jump to protected mode. Depends on how you want to do it. I think I'll read the disk, then jump to protected mode. Okay, then finally, we'll call the C function. I think I'll call it kernel main. So to understand the GDT, I think I'll just use a different file. I'll call it GDT. So all processors have things called system data structures, where you store some information about the processor. For example, how is memory used? How does memory work? For example, let's say if you're on 64-bit, then you have something called paging. Then one of the features of 64-bit mode is the memory of one process is protected from the memory of another process. So we'll call it protected process memory. That means process 1 cannot access process 2. Cannot access the memory of process 2. Then another thing is a process cannot access memory of the kernel. Any process, let me say any mode process cannot access kernel memory. So this is a protection mechanism. So to be able to do this, for your processor to be able to enforce this, it needs data structures that will tell it which memory addresses are accessible from which ring. So in the beginning, we had something called, let me call it was real mode, the mode you are currently operating at. So the way it worked is you had something called GDT descriptor. I think I prefer GDT descriptor. Then you had a base, then you had a limit. So the base was the beginning of a memory address. So let me just use that 16. So what this entailed was that the base told you which memory address or the beginning of your memory location, memory begin. Then the limit told you the size of the memory, size of the memory. So with these two information, you could know the entire memory range that you have. For example, if you want to know memory end, it is equal to base plus limit. And then what the processor did was to check if maybe memory access, memory dot, let me call it access, which means it could be read or write, is greater than base plus limit. So this just means if you're trying to access memory outside your range, then the CPU will raise an exception. raise an exception. So in CPU lang, an exception is normally called as an interrupt. So think of this like maybe a Python exception where if you have a list, or maybe Java, if you have a list and then you're trying to access something out of bounds, it will raise an exception. But the processor still needs a way to enforce such things. That means, for example, if you're in user mode, then you'll be allocated a base of your memory range and a limit. That means anytime a user mode process tries to access memory, then the CPU or the processor will check if you're within the range. So it will check if you're trying to access more than the base plus limit, then it will raise an exception. Or if you're trying to access less than the base, then it will raise an exception. This was in 16-bit mode. Then in 32-bit mode, they had to extend the structure. So now a descriptor had base. A descriptor had a base, then you had to they had to increase. Okay, no, I think I misled you. This was 16 bits because we're in 16-bit mode. Now in 32-bit mode, you have 32-bit addresses, so they had to increment it, but they can't change the structure because of backward compatibility, so they had to make the structure kind of funky. So I think we have 16 more bits for base. Then you have U8 for base again. So base just means the base of the beginning of the memory range that you have been allocated to. And then we have something called access. I'll talk about it. Then finally we have something called base and I think limit. Let me just check. So I think I should share my whole screen. Okay. So let me look GT. So again, you don't need to cram the structure. You just need to understand. If you can see it, if you see the structure, you need to understand what the fields entail. So in this case, let's wait. Okay, this is the GT descriptor. So we see we have limit, then you have base. So these are 16 bits, 16 bits. Then you have base again, which is 8 bits. Okay, so I was kind of around there. And then you have this access byte, which is 8 bits. Then you have limit again, which is 4 bits now. And then you have flags, and you have base again. So let me just rewrite this. The reason why it's spread out like that is because the structure started as follows. Then in 32-bit mode, they had to extend it because base now needs to be 32 bits. So we see we have limit. That means the first thing, then base is 16 base. You already have it. Then you have 8 bits base. So here, so we need to encode it in our structure. Yeah. And then the next thing is access. And then we have limit and flags. It's not based on flags, limit and flags. And then finally we have base. So if you see base has 32 bits, have base which is spread out from here, here, and here. Then this access byte, which is one of the most important things, just tells us the different flags. For example, P means present bit. If this flag is set, it means this segment descriptor is active. So the CPU won't ignore it. If it's 0, CPU will ignore it. Okay. Then DPL means the current privilege level. The last time, I think the first session, we talked about rings or privilege levels. Pardon? Someone is talking, I can't hear you clearly. So DPL just means the ring that you're executing at. So Intel has 4 rings. We have ring 0. Okay, there are other rings above ring 0, but as far as kernel development is concerned, we have ring 0 to ring 3. Ring 0 is the kernel mode. Ring 1 and 2 meant to be for drivers, but no one uses it actually because it's so expensive computationally. Not used. And then ring 3 is now the user mode. So DPL just gives it, if it's 0, it means it's kernel mode. If it's 3, this is a user mode segment descriptor. Then S signifies the descriptor type. I'll talk about it later. But for now, we don't really care about it. Then you have execute bit. So for example, in Linux or whichever operating system you operate on, you have things, for example, you can have memory that you can't execute. You can have memory that you can read. Let me give an example of code section. So code section is where your code is stored. Your code stored in memory. So this needs to be readable and executable. But most systems enforce that it's not writable, because if you can modify your code on the fly, then things get messy. So execute bit just means, is this memory allowed to be executed? If it's not allowed to be executed and someone tries to execute it, then it will raise an error, an exception. Then we have read write. Read write means different things depending on the descriptor type. So we have code descriptors, you have data descriptors. So code descriptor carries the selector for the code section, and then you have data descriptors which carry the section for data segments. So if this is a code how do you call it, code descriptor, then if read write is set, then read access is allowed, but write access is never allowed because it's code segment. Then if it's data, then if it's set, write access is allowed, read access is always allowed for data segment. And then you have access bit. Access bit just entails or just tells you if or indicates if the memory has been accessed. Then what else? We have this direction flag. For example, if you know anything about the stack, you know that in Intel, the stack grows downwards. So this DC means direction bit, which just indicates the direction in which memory grows. So if it's zero, the segment grows upward. So from 0 to the maximum. If it's 1, then the memory grows downwards like a stack. Okay. Then limit just indicates the highest, the limit, the biggest size of the memory. Do you have any questions about the GDK selector?
No.
Okay, this is one of the hardest. So if it's clear, then the next thing is just to see how you load it. So these selectors, they are like, I think I misled you with the terminology. So we have these GDT descriptors, and then you have something called GDT. So GDT stands for Global Descriptor Table. So you see, it's a table containing these descriptors. You can think of it like an array. In fact, in C, we'll just create GDT descriptor, and then we'll call it GDT, and then it will be an array of these things. So the GDT, the global descriptor table, contains the GDT descriptors. So, so what you need to do is create the GTs and then store them inside this array. So the Intel mandates that the first GT descriptor must be 0. Everything is 0. And then if you check this structure, we have, let me just use the structure I wrote in or whatever. You have 16 bytes, then you have 16 bytes, that's 32 bits, and then you have 16 bits, then so the total size of this structure is 8. So we have 8 bytes, which is 64 bits. So the index of the first element in the array, GDT array, will be offset 0. Then the next one will be plus 8 because the size is 8. Then the next one will be 16, then 24. So we need to decide how many GDT descriptors we want. The null descriptor is a must, so we need to create a descriptor having zeros in all these elements. And then we can create a data descriptor and then a code descriptor for now. And then we load it to memory. So to load it into memory, we just need an instruction called load GDT. It's called load GDT. And then we'll pass it the address of this GDT. Let me just make it like in C. GDT, let me call it array. And then that will be it. So the hard part is just filling out these GDT descriptors. So let's go to our assembly and start filling it out. I'll reference this table. I do want to put it. Let me put it here. Okay, so remember each entry is 8 bytes. So if you are working in C, we could have created a structure, or we could have created just a 64-bit integer and then filled the bits manually. But in assembly, I think they have syntax or syntactic sugars for creating structures, but really I don't know about them. So we'll just define bytes, not code bytes, and then let's call this code descriptor. Let's start with null descriptor. Null descriptor. Then what we'll do is define zeros. So remember, the null descriptor just has to be zeros, and because DQ means define 8 bytes, then we have defined 8 bits of 0, so that's done. Then the next thing should be, is it data or code? Thanks. Let me just check for my convention. I want to stick to it. Let's just first fill it, and then I'll see whether I always start with data or code segments. Let me start with code. Oops. So let me do it code descriptor. And then I'll say DQ. So now we need to fill in these things. So limit will be will be the maximum, the maximum, which is 0xf 0xffff. Let me just show you. So it's 16 bytes, 16 bits. So 2 power 16. I think -1. This is 65, 535, and then let's do it in hexadecimal. Oops, we need to kind of slow. So it's 0xff. So we'll do 0x, and it will be FFF. That will be the bottom 16 bytes, 16 bits. Let me just call them 2 bytes. And then base will be 0. All the base will be filled with zeros because we want our memory to begin at the beginning. So the next thing will be 0, 0, 0. Then let me just do this. Then you have another base, which is 1. You have 2 zeros. Remember, 2 hexadecimal digits equals 1 byte. So that's why I'm doing it. And then the access byte, we can, let's read about them. So we have access bit, will be set, this means, blah, blah, blah. So we'll set it to 1. We'll set access bit to 1. Then read write, because this is code segment, we'll also set it to 1 to allow read access. And then this direction field, we'll set it to 0. We have DC and conforming bit. Yeah, I think the videos are being recorded, so you can go over them. I think we'll set the direction bit to 0, and then we'll set this to 1. So, and then this DPL will be 0. Remember, 0 means kernel mode, and then 3 means user mode. We haven't gone into user mode yet, we're still in kernel mode. And then this type we'll set to 1 because we are defining a code segment. Then P must be 1. So let's think about the bits. So let me just prototype here. Access is 1. Then read write is 1 bit, so we need to set it to 1. Then DC is set DC 2 bits. It's kind of confusing, but we'll set it to 0. Then executable bit will be set to 1. Then system will set to 1 because it's code set. TPL, it's 2 bits, so we'll set it to 0, 0. Then finally we'll set it to 1. So this is 11. I think it's 11. This is 9. Is it 9? This is 8. This is 9. Then this is 11. So in hexadecimal, it'll be something like 9. Then this will be A. So here I need to put 9A. 9A. Let me stick to my lower character thing. And then limit will be FF. Will be F because it's 4 bits. And then flags, where are the flags? We didn't look at the flags. So we have this thing called granularity, and then we can simply ignore it, but we'll set it to 1. And then TB size. So this size flag defines if it's a 32-bit mode segment or a 16-bit mode segment. So we'll set it to 1 because we want 32-bit mode. And then L specifies it's 64-bit mode. We don't care about 64-bit mode. So we'll set it to 0. So let's prototype it. So we have 4 bits. Granularity, we'll set it to 1. TB, we'll set it to 1. And then long mode, we'll set it to 0. Reserved, we'll set it to 0. then this will be, this is 12. Is this 12? It's 8, this is 4, 12. So that's B. And then we have flags, then we have base, which is 0, 0. So we need to set here 0, 0, then B. 10, 11, 0, C. I think I confused base with flags. We have limit, then we have flags. So let's check where is the limit. See, yep, it's fine. Then the next thing is base, it's 0, 0, 0. So let's count if it's 8 bytes. If it's 8 bytes, yeah. So 1, that's 2, 3, 4, 5, 6, 7, 8. Then you need to do the same for data segment. The only thing that will change is the access flag. Now instead of execute, this should be 0 because we don't want a data segment to be executable. So execute is put 3, 0, 2, 3. We need this to be 0. Then that's then let's look at the access. Let's put that 0. I think we can leave it to 1. Let's see, but I have a feeling I normally put it to 0. So now we just need to change this to be 3. We'll change this to be data. So I can safely remove this. Now that we have filled the descriptors, do you have any questions up to that point? So I wanted to check how I normally do it. So let's see. Check this one. Hold on. 1000. So you have 0 XFF for the code segment, you have 0, 0 for the base, you have main A for the flags, and then 0, 0 for the base again, then you have 0, 0 CF. I think I've done it right. You have 0 XFF, you have 6 zeros, you have main A, then you have CF. Okay, that's the code segment. And then let's check for the data segment. You have 0 XFF, 0, 0. I have this main 2, but I have done main 3. I don't think it will be an issue. Then CF. So now the only thing that remains is to create an array, a structure. I think I forgot to mention this. Let me go back to gpt.rs. So the way the gpt works, And the way this processor expects this structure to be fast is to be passing something called GDT register. Let me call it GDT register. And then it'll just have the base of the array. So let's call it Q32 base. Then I'll comment it. This is the base, the GDT array. And then it'll give it the size so that it can know how long is this array. Otherwise, it can access out of bounds. We think it's 16 bits, and then we call it limit. It's also called limit. So now we just need to create this, and then we'll pass this GDT register to log GDT, which is where I got from, where I went from. So like that. Let's check if they raise the same issue again. They don't, but that's how you should do it. Let me check. Let's just do it. Don't see. So what we need to do is simple. Oops. Just create GDT. We call it GDT register. And then inside we'll just define W. W define double word. So the limit comes first, and the limit comes first. Okay. Wait a second. So we'll define what, then the limit will be, the limit is the size. So the size is from this location to this location, and then -1, because it's zero-based indexed. So if you have, for example, if you have an array of 4 elements, and then it's 4 minus 0, and then -1, that's the maximum size, because the maximum size is 3. So we'll just do GDT register minus null descriptor, then -1. Then we'll define double word now, null descriptor, because like the base of our array. In fact, you can take this down there. We create other data stuff. So now we just need to create a function called load_gdt. Load_gdt. And then we'll pass the base of this GDT register inside array X. We don't need to do that. We can just do load GDT directly. What did we call it? So we need to pass this address. So GDT register, let me just copy it. I wanted to pass it as a parameter so that we can reuse this function later on in C, but I think we can just rewrite it again. GDT, then let's return. Let's confirm we have done it right. GDT, how to pass in the S, okay. Though I'm not sure it's necessary. Okay. Then you need to call it from enter protected mode, from switch to protected mode. So we just need to call it before. So let's call then finally we need to do a far jump to protected mode. What we'll do at this point is we'll just have another label. Let's call it pmode start, just to test that we have entered to 32-bit mode. Let me do something like bits. So to tell the assembler that we are now in 32-bit mode, and then we just jump current. Okay. So if we do anything wrong, the OS or the system will just crash. But if we just hang, then we have entered to protected mode. So the last thing we need to do is to alpha jump. I'll explain what alpha jump is. Jump. Is 08 pmode begin. Pmode begin or pmode start? I don't really remember. Start again. Okay, let's try to run it. See what happens. Okay, so it doesn't crash. That's a good sign. So before I do some cleanups, I just want to confirm that we are actually in 32-bit mode. So what I'll do, I'll try to write to the screen. I'll try to call an interrupt. So let me call it 0x10. And that should make it crash. Yep, you see it's crashing because once you enter the 2-bit mode, you can't call BIOS interrupts. So that means in the 2-bit mode. So what you can do is maybe try to print to the screen. I'll explain why I'm doing this. 0. Four eight decimal. 4.8 hexadecimal. Oops, 65. Which one? Okay. Okay, so it actually works. So let me try to explain everything now. So once we jump to this, I haven't explained what a far jump is. So let's go back. So we said today we need to understand and load the GPT. We think nobody has raised an issue there. Then we need to read to the disk. We haven't done that. We'll do it. And then you need to jump to protected mode. We have done that. And then you need to call kernel main, which we haven't done that. So in the process of switching output in the system expected set, we had to switch to protected mode. And to do that, we needed to disable interrupts, set up the A20 gate, which I explained last time, set up video mode, then set up some data structures, which is GDT. I've done that. Then set up pmode bit. We did that last time. Then jump to 32-bit mode. So to tell the processor that you need that the mode has switched, you need to do something called a far jump. It just means you give it the segment and then you give it the label. So the segment in this case is the code segment. But remember, we created a code segment here. This one is why you need to create this. So the reason why I passed 0x08 is because this is index 0 and then code segment is 0x08 because these segments are 8 8 bytes long. So the next index is 8. So that's the code segment. So when you execute a far jump, the processor will look into the GGT at the index you've given it, and then it will use that segment as the code segment. So now our system uses this GGT descriptor that you've set. You can't print using BIOS. The way it works, or the mode that you've set up is called, how is it called? You're using VGA, and you're using this resolution. It's 80 times 25 times 2. So what this means is that the width of your screen is 80 pixels, then the height of your screen is 25 pixels, and then the depth is 2 bytes, 2 pixels. So this depth means that 1 byte is used for the color, the other is used for the character. So to write to the screen, we just need to write to the memory location allocated for the VGA. So that memory location in this mode is 0x B800. So in this case, the first byte or the lower byte is the character, then the high byte is the color. So in this case, the color I passed in 0x07. I don't know. I think that's the default color. If we change it, let me try 5 and see what happens. Let's run. You can see the A at the beginning is color magenta, I think. So that's as easy as it gets. To write to the screen in this mode, you just need to write to this memory location, and then that's it. So let's try another color. Maybe let's try A. That's 10. I don't know if it's a valid color, but we'll see. So that's green. Now we can do a similar thing to what we did here when we created a write car function. But in this case now, we need to track of different things. We need to keep track of the index. So let me just try to write it. How will I call it? Let me call it podcast. So remove the I think this one actually should have been and 0x800, and then you need to pass it the color. So where will you pass the color? I think we'll pass the color in EAX. We'll pass it in EAX. Let's just pass it in EAX. We'll think about the rest later. So EAX, then let's write. But also you need to keep track of something called the index. For example, if you just keep on writing to this location, we'll be writing at the first location, or at the beginning of the screen, so it will be somewhere here. So when you write, we need to increment the pointer to the next thing, to the next thing, to the next thing. So in this case, you need to think of some way to do it. Let me just create a variable. We call it index, and it will be 1 byte, and it will begin at 0. Then we'll do really do we call it bx, then we move I'm going to explain what I'm trying to do in a few. Then move So what I want to do is to create this variable which where we are. So at the beginning we print, the index will be at 0, so the current print will be at that location. And then after that, because the column must pass the index into BL to the EBX register, and then we add it to this. So at the beginning we'll be adding it to 0, then we'll increment EBX by 2, then we'll store that result inside index. So essentially it will be like, maybe let me try to write it in C. It will be something like 0x b800 plus index, let me say plus bl equals, so assumes this is a pointer, and then you're adding an offset, and then you want to write ax. Then the next thing you do is you, and finally we store bl inside index equals bl. Then you have updated the counter, so the next time this counter will have been increased. That's what I'm trying to do at this point. So we need to move inside dpx index. Then we have to call put car. But also need to move the character to right hand side. X will do 0x 08. Put on. Let's try with that and see what happens. Invalid defective address. Line 156 site number. Do X. Okay. Okay, that works. So to load the value of index, we need to dereference it to read from memory. So we need to use these brackets, and then we need to load it into the lower byte of